Now we're only going to talk about part of kinetics today because this packet does not have the integrated rate laws in it. Now there's not much to the integrated rate laws, and they're a lot easier than the book makes them appear, but a good portion of the questions on the AP exam will be about the integrated rate laws. Especially being able to look at a graph and to tell whether something is zero order, first order, or second order integrated rate law. So on the formula sheet that you have, you may just want to circle or highlight the kinetics formulas. They're not labeled. Yeah, grab a packet and welcome. There are a lot of different algebraic forms of the formulas, and it really doesn't matter which form you use. But it is nice to know that if you needed to do some calculations with an integrated rate law, that the formulas are there. They're just not labeled. So the first one is the first order integrated rate law. And once in a while, a calculation needs to be done for that. We have not seen a calculation needed for the second order integrated rate law in about 15 years. And that was only like once in the last 30 or 40 years of tests I've looked at. But because they have it on the formula chart, it means that it is definitely fair game. Zero order integrated rate law calculations are not on the formula chart, so they won't have to be done. The first order half-life equation is on your formula chart, where half-life is equal to 0.693 over K. Where did the 0.693 come from? Anyone know? It's the natural log of 2. And you may be working with something similar to this in an Algebra 2 class, but half-life is equal to 0.693 over K. Something else to remember that's not in your packet but has been tested a lot lately is that a first-order half-life is the only constant half-life. Zero or second order, the half-life changes. But for a first-order reaction, the half-life is constant. All nuclear reactions are first order, and they have a constant half-life. That means that the concentration is cut in half at that time period, and then cut in half again at another one at the same time period if it's first order. So if you're looking at a graph and you see that the concentration is cut in half at equal time periods, then you know it's first order. Okay, little k is the specific rate constant. Of course, t is time and t sub 1/2 is half-life. So know that you don't have to memorize the formulas for the first and second order rate laws. They are on that formula sheet. Okay, chemical kinetics does not have anything to do with thermodynamics, really. Here we have a diamond oxidizing, burning to make CO2. The delta G value, have you had delta G yet? Okay, delta G is a measure of how thermodynamically favored or spontaneous something is. If it's negative, it means it will work. It is thermodynamically favored. This has a negative 396 kilojoule value. That means that it's going to happen. But do diamonds change into CO2 quickly? No, it's really, really, really slow. Even though when you calculate delta G, when you do thermo, it's very thermodynamically favored. Whereas a hydrogen ion combines with a hydroxide ion instantly to make water in a neutralization reaction. That has a negative delta G, but it's not nearly as negative. So just know that thermodynamics tell us if a reaction can occur, and kinetics tells us how fast. Some reactions that are thermodynamically feasible, like a diamond oxidizing, are so slow kinetically that we don't ever see that happening. And that would be good. Our diamonds wouldn't be very valuable if they quickly turned into CO2. The factors affecting reaction rate. This is tested a lot on the exam, and it is very easy. However, your textbooks don't put this in a nice, neat little package. So really, really important to know this. If you increase the temperature of a reaction, the rate's going to increase. Why? Two reasons. Tell me the two reasons why increasing the temperature that a reaction's at will increase the rate of the reaction.
Well, the molecules are going to go faster since it heats up.
Okay, the molecules are going to go faster because they have more kinetic energy. What do molecules have to do in order for a reaction to occur? Collide. They have to collide. So they're going to collide at greater velocity. And they're going to collide more frequently. So they collide with more force and more frequently. So those two reasons are why reactions speed up at a higher temperature. The nature of the reactants. What the chemicals are is going to determine the rate of a reaction. Concentration of the reactants. We know that there are more collisions the higher the concentration is. So the AP exam might ask you to explain something using collision theory. So you're talking about what's going to cause more collisions, what's going to cause more forceful collisions, and things like that, if they ask you to do that. So increasing concentration increases the rate. Adding catalyst will increase the rate. And there are different kinds of catalysts. We'll probably touch on at the end. Increasing the surface area increases the rate of a reaction. We know that we start a fire with kindling or something that has a large surface area rather than trying to light a log, because greater surface area causes more collisions. Inert gases, adding an inert gas does not affect a reaction rate. But sometimes they will throw that in to try and mess you up. So those factors affecting reaction rate. Have any of you in your classes looked at the TED Ed Kinetics video? It is awesome. It takes 5 to 10 minutes. It is funny. And it teaches this factors affecting reaction rate in a cartoon method. Is probably it's probably the best chemistry video I've ever seen in teaching something quickly and enjoyably. So if you just Google TED Ed Kinetics, it will show up, and show up on YouTube or any place. And that was it, but we don't have time in 50 minutes to watch. Okay, so molecules have to collide in order to react, but not all collisions are effective. The molecules have to collide with sufficient energy. They also have to collide with the correct orientation. Now, if we're talking about two spherical hydrogen atoms colliding to make H2, it doesn't matter how they hit each other as long as they have enough energy. But if we're talking about more complex, especially biological molecules, they've got to fit together correctly. Not every collision is effective. And sometimes it's going to take a surface catalyst or something that one of the molecules can absorb on the surface of in order to facilitate that. So two factors for effective collisions: sufficient energy and proper molecular orientation. So if the Br and O molecules collide this way, we can get Br2 and 2NO. Or this way, we can get Br2 and 2NO. But if they collide with the oxygen ends, no reaction. A reaction diagram like this is commonly seen on the AP exam in several different topics, really. And we don't see a whole lot of those in most of our textbooks, so it's real important that we know, that we understand them. We've got the energy of our reactants here, the energy of our products here. The height of the hill from the origin to the peak here is the activation energy. It's the minimum energy that colliding particles have to have in order to react. If they don't have that amount of energy, no reaction is going to occur. And at the peak of that hill, when they collide, at the instant of collision, they often form a temporary high-energy complex called a transition state. Some books call it an activated complex. Doesn't matter. Sometimes the products have lower energy than the reactants, and sometimes they have higher energy. Does this diagram show an endothermic or an exothermic reaction?
Exothermic.
It is exothermic because the products are lower than the reactants in energy, and that means that energy is released. In an exothermic reaction, energy is always released. Every once in a while, we'll see one where the reactants and the products have equal energies, but that's quite rare. So the rate of the reaction does not depend on the height of this hill. I'm sorry. Let me back up. It depends on the height of the hill. It does not depend on how much energy is released or absorbed. Because if the particles don't have enough energy to get over that hill, if they don't collide with that amount of energy, no reaction is going to occur. So the lower that hill, the faster the rate of the reaction. So sometimes we add a catalyst that has a pathway with a lower activation energy. And so the reaction speeds up. So the higher the activation energy, the slower the reaction at a given temperature. So the molecules and the collisions have varying energies. Not all the particles have the same kinetic energy. They're pretty much all at the same temperature, but you're going to have a great variety of energies. The higher the temperature is, the greater the variety. So as temperature goes up, more collisions will have enough energy to overcome the activation energy. If we look at this, T1 and T2. Which is higher, T1 or T2? It looks like T1 is higher because the curve is higher, but that's not what the graph is showing. This is showing the number of collisions having a certain energy. The area under the curve in each of these is the same because there's the same number of particles, but T2 is actually the higher temperature. More particles in T2 have a higher kinetic energy. So more of them will have the activation energy, and the reaction rate increases. Always, always, always read the axes on a graph when they ask you a question about the graphs, because many of them look similar, but they show different things. So you've always got to read the axes rather than assuming what something is. So T2 is higher than T1, even though the peak is lower there. All right, raising the temperature of a reaction almost always increases the rate. What's the best explanation of this phenomenon? So read through those answers and pick the best answer. Okay, the answer is and it's okay to be wrong. You're not taking a test here.
A or D,
D.
D, wait, I didn't read D.
Okay, first of all, is A correct?
Yes.
Yes, but is it the best answer?
No.
No. Now, if you just started reading through and you saw A and it was correct, a lot of students would put that down and go on to the next question. You can't do that on the AP exam. You gotta go through all of the choices. It's correct, but it's not the best explanation, because the best explanation is that they both collide with increased energy and with greater frequency. So D is the best answer. So you always have to read through all of the answer choices. Now, if you don't know the answer for sure, if you can just say it's A or D, should you guess on the AP exam? Yes, you should always guess. There is no guessing penalty. But if you're not sure of something, circle your question number, because you're going to go back to that after you finish the rest. And you should have time for that. Also, if you're very slow with math, you may want to take something that you think has extensive math and put a star by it and go back to those later to make sure that you've got time to do all the easier questions. You know, use some good test-taking strategies. So D was the correct answer. Okay, reaction rate is the change in the concentration of a reactant or product per unit time. Reactant concentration always decreases. Product concentration always increases over time. When we put the brackets around something, it means the concentration in molarity. So here the rate is equal to the change in the concentration of A over the change in time. If it involved a reactant, it's going to be negative because the concentration is going to decrease. And this gives us the average rate over that time period. Does rate increase or decrease during a reaction? Increase or decrease? Or does it stay the same until the reactants are all used up? It's going to decrease because, okay, think about it. You've got more reactants at the very beginning, right? But your reactants are going to start getting used up. So your concentration of reactants goes down as the reaction progresses. So the reaction rate always goes down as the reaction, as it progresses. Think about a battery. You know, the voltage that a battery produces decreases as the battery is used. It's a chemical reaction. The reactants are decreasing. Here we have the reaction where 2NO2 decomposes to 2NO plus O2. The NO2 decreases here. That's the green line. The NO increases. That's the blue line. And the O2 increases. That's the pink line. Why does the NO increase faster than the O2? There's two of them, right? Okay, very good. Look at those coefficients. They tell us so much in AP chemistry. I know my students often didn't think something could be that easy. That just looking at the coefficients, you could understand what the reaction was going to be, or what the answer to the question was going to be. It was AP chemistry. It had to be some fancy equation that you plug things in. But often you're just looking at the coefficients in the balanced equation. So 2NO2 yields 2NO and O2. These both have 2's, so the NO2 decreases at the same rate that the NO increases. And the O2 increases half as fast because the coefficient was 1 compared to 2. Okay, so here we have a reaction where oxygen gas is consumed at a rate of 0.036 moles per liter second. What's the rate of appearance of N2O5? So we're given the rate of disappearance of oxygen. We want the rate of appearance of N2O5. calculator. And again, don't worry about making mistakes this morning. We want to get all those mistakes out of the way, so you're not making them on your exam or the AP test. Answer is? 0.072, right. If the oxygen with a coefficient of 1 is disappearing at 0.036, the N2O5 must be is appearing at twice that, 0.072. Okay, then the rate of consumption of NO2. Okay, it's going to be consumed 4 times as fast as the oxygen, right? So 4 times 0.036. Okay, so we have a similar question here. We want to determine which answer is correct. Answer is? C. Very good. Now, to get an instantaneous rate rather than an average rate, what we were talking about was an average rate. If we needed an instantaneous rate, we compute the slope of the tangent line, the line tangent to the curve at that point. So here we had, at this instance, we have a rate of 5.4 times 10 to the negative 4 moles per liter second. And down here we have a rate of 2.7 times 10 to the negative 4 moles per liter second. The rate decreases over time. Now we're going to be working right now with reaction rates that are initial rates, where very soon after you've added your reactants. And it's before the reverse reaction has started happening. Okay, we talk about a differential rate or an integrated rate. Neither of these require calculus. We can talk about the integrated in calculus terms, but we don't need to. Okay, so for a differential rate, if we had this reaction 2x plus y yields z, we write a generic rate law, where we write rate is equal to little k times the concentration of the first reactant raised to some power times the concentration of the second reactant raised to some power. Those powers, which we call orders, have to be determined experimentally. It's not like an equilibrium where we're going to raise them to the power of their coefficients in most cases. We have to look at experimental data to figure out what those orders are. Now the overall order is just the sum of the individual orders. The orders are usually small positive whole numbers, but they can be 0, they can be negative, they can be fractional. Not very often, but we have seen an order of -1 or an order of 1/2. But usually they're going to be 0, 1, or 2. So the value of K depends on what the reaction is, it depends on the temperature, and it depends on whether we have a catalyst or not. Faster reactions have larger K values. So if this reaction, the order is understood to be 1 for A, 2 for B, and so 1 plus 2 is 3, it's third order overall. It's always nice when they ask for the overall order, because that's very simple. Now the units for K. Very often they're going to ask you specifically for the units for K, and that is going to be the whole point. And you've got to use your algebra to figure that out. Except there is a shortcut that you can use if your brain's a little fried on the exam and you don't trust your algebra, the shortcut is nice. If I were just to take that previous rate, right there, that rate law, rearrange it to isolate K, and so our units, our rate was moles per liter second. Concentration here is moles per liter. This is moles per liter times moles per liter, so moles squared per liter squared. If we were trying to simplify that, we get rid of this mole and this mole and this liter and this liter. The liter squared goes into the numerator. The reciprocal second goes into the denominator. So we end up with a liter squared over mole squared seconds, which can also be written as molarity -2, seconds -1. That's the algebra. The shortcut is that the units of K will be liters to the x over moles to the x times whatever unit of time you were using. The value of x is 1 less than the overall order of the reaction. So if it was a second order reaction, 2 minus 1 is 1, and it would be liters to the first over moles to the first times seconds or whatever unit of time you had. So on this one, overall order was what? Third. Okay, so 3 minus 1 is 2. So liter squared over mole squared, seconds or hours or years or whatever. Using experimental data to find your rate law. Now some of you that have gone through this is going to be easy peasy. Those of you that have never seen it, we're going to start with a simple one. And those of you that haven't seen it before, it takes a little bit of practice, but with that practice then it becomes pretty easy. But we may not, you may not master it today, but it'll give you an idea of how to do it. With the differential rate law, we have multiple experiments where we vary concentrations of reactants in each experiment to see how that affects the rate of a reaction. With an integrated rate law, we have a single experiment where we watch the concentration change over time. So if you know you have a question that is kinetics, look, do you have multiple experiments? Or do you have one experiment with data being measured over time? If it's multiple experiments, you're using a differential rate law. If it's a single experiment, that's an integrated rate law. So if we decide to double the concentration of a reactant, and doubling that concentration causes the rate to double, we know it's first order in that reactant. And this may not make a whole lot of sense till we look at some data for those of you that are new to this. If we double the concentration and it causes the rate to quadruple, then it is second order. Because concentration was times 2, rate is times 4. 2 to the what power is 4?
Second.
2 to the second power is 4. If we double the concentration and the rate doesn't change, then it's 0 order. Because 2 to the 0 is 1. And we usually take that reactant out of the rate law. So starting with something very simple, here we have 3 experiments. We know that this is a differential rate law experiment, or type problem. We have concentrations of A and B. Now, in a good experiment, we always have control. Now, you'll find that sometimes they don't have a control, but they should have a control. All right, so if we look at experiments 1 and 2, A is a control because it was held constant, and we only changed B. What effect did doubling the concentration of B have on the rate? It doubled it. Now, your textbooks and your Nmsi packet are going to show you what we call the ugly algebra method of solving this. I think it's much, much easier to use chart logic, so we're going to look at that. If we write our generic rate law, not knowing what x and y are, we look at experiments 1 and 2, A was constant, B doubled, that caused the rate to double. 2 to the what power is 2? 2 to the first power is 2, so we know that the one we changed, which is B, is going to be first order, right? Now we need to figure out what A is going to be. So we need to find a place where B stays constant. So that would, in this case, that would be experiments 2 and 3. B stayed constant. A did what? Doubled. And that caused the rate to quadruple. And 2 to the what power is 4?
2.
2 to the second power is 4. So what order is A?
Second.
A was second order. All right, we're going to look at, we're going to look at this one. Figure out the rate law on this one. So, on your paper, write your rough rate law and figure out what the order is for A and for B. In real life on the AP exam, they might not always be doubling something. They might be tripling something. If you triple a concentration and the rate is 9 times greater, what is that telling you? 3 to the what power is 9?
Second.
Second is second order. And if it looks like they're cutting the concentration in half, go the other direction. It's easier to look at, you know, going up then. Is it doubling? Okay, on this one, what order did you get for A? 0 is correct. Let's look at Y. Okay, B was our control. It stayed constant. A doubled. And that did not cause the rate to change. So doubling A has no effect on the rate of the reaction. So A is 0 order. For those of you that have had all of kinetics, that means that A is not in your rate determining step. Okay, then to figure out what B is, we want to find a place where A is constant, which would be 2 and 3. They're not always next to each other. And B doubled, which caused the rate 2. And that means that B is what order? First order. Good. So your final rate law, simply rate is equal to little k times the concentration of B. Now, it would not be wrong to have A to the 0 power in there, but normally we take it out if it's 0. And it doesn't matter whether you put the 1 there or not. It's understood to be 1 if there's no other number there. Okay, harder one. What's the order of A? 1. Okay. Very good. What's the order of B? 0. All right, this was a poorly designed experiment because there is no control to figure out B. We can figure out A easily because B stays constant, A doubles, and the rate doubles. So we know that A was first order. Already knowing that A was first order, since in experiment 2 and 3, A doubled and B doubled, and the rate just doubled, the doubling was due to A. And so B must have had no effect. And so B is 0 order. What if this had been 0.8? It had quadrupled. Then B would also have been first order. Very good. It is rare that they ask one like that, but they certainly can. Okay, now, more likely, you will see things other than A and B, and you will see numbers that are not quite as pretty as I've been putting up there before. And you may have to round them a little bit because they're not going to be perfect. It's experimental data. Our experimental data is not going to be nearly this perfect. So go ahead and round things off. When you have numbers in scientific notation, make sure that they all have the same exponent. Often they do not. So you've got to really look at things like that. We're not going to go through this one right here. But if you already did, it is, whoops, sorry. It is first order in each. Okay, here, well, let's see. Let's look at this one, because this is the hard one. Now, those of you that are seeing this for the first time, this is not something you would do on the first day of the unit, all right? Okay. But those of you that have been doing it, if you can do this one, you can do any of them that they throw at you. First of all, notice they are not pretty numbers. Round them off. Make them pretty numbers. So where you've got 10 and 20 and 40 and 2 and 4 and 2. What order is A? A is second order. Good job. Okay, we're not comparing experiments that are right next to each other. But we need a control, and that's as close to a control as we have here. B is relatively constant. And we quadruple our our concentration. And the rate was 16 times greater. 4 squared is 16. So we know that A is second order, sorry. Okay, figure out what B is. There's a couple ways to do it. Any ideas? Go ahead and answer. Is it first? Second? Okay. You guys gotta be more confident in giving an answer. Doesn't matter if it's right, okay? This is not I'm not judging you. We're trying to get all the wrong answers out of here. It is second. Now let's figure out how we could determine that. We look at first two experiments, we're doubling A and we're doubling B. Now we said that A was second order. So doubling A would have what effect on the rate? Just doubling A by itself, if it was second order. It would quadruple it, right? Okay, and it didn't go from 5 to 20, it went from 5 to 80. So it was 16 times greater. So it must have been quadrupled twice. Another way to look at that is to look at experiments 2 and 3. Here we're doubling A, here we're cutting B in half, and our rate didn't change. That tells us they had equal and opposite effects, that A and B had to be the same order. And since we already knew that A was second order, B must also be second order. Now, I doubt you'll get one that hard, but if you can handle this, then you're good on these. Okay. Let's skip some of these. All right, we're going to look at this one. Particle view questions are important. I want you to be comfortable with doing math on particle view multiple choice. Students often think that they don't need any math for them. That it's particle view, it must be super, super easy, but not always. Okay, so here we have a reaction 3x plus y yields z. X is the triangles and y is squares. These represent the reactants in trial 1, 2, and 3. We know the rate of the reaction for trial 1 and for trial 3. It says it's first order in X. We want to know the rate for trial 2. So we want to look at how the numbers change. So we got to count everything. We know in trial 1 we had 6 X's and 6 Y's. In trial 2 we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 X's and 6 Y's. So what was the control here, X or Y? Between these two. Y stayed the same. X doubled. It was first order in X. So what should the rate do? If I double the concentration of X, it was first order in X, the rate should double, so the rate should be 0.20. So C was the correct answer. We're going to skip that one. Okay, reaction mechanisms. Most reactions do not occur in a single step, as we've seen in our chemistry textbooks since we started looking at chemical equations in elementary school. They're all written in one step. Most of them are not that simple. They occur in a series of steps called a reaction mechanism. But most of the time that reaction mechanism cannot be proven because the products of the steps of the mechanism only exist for fractions of a second. But there are thousands of chemists whose life work is trying to determine the mechanism of a certain reaction. Because if you know that mechanism, you can control that reaction.
This group is pretty easy. The chemistry, there are only 2 groups, so y'all are going to go 9, 5, 9, 5. But here's the card. We forgot.
All right. Thank you.
All right.
Because if you can control a mechanism, you can control something that causes a biochemical deficiency, or you can produce something. There's a lot of good that can be done by figuring out reaction mechanisms. In a reaction mechanism, we always have intermediates. Those are temporary products. It's a product of one step of a reaction that's used as a reactant in a later step. If something is an elementary step, that means it does occur in one step. And a mechanism has multiple elementary steps. We can write the rate law for an elementary step from its coefficients. Catalysts are going to be reactants in one of the first steps of a reaction that will be used up but will be produced again in a later step. As far as most catalysts are concerned, some are surface catalysts, which behave a little differently. The slowest step in a reaction mechanism is called the rate determining or rate limiting step. It's like the slowest step in an assembly line. It's going to limit how fast your products are made. It's going to be the step that has the highest activation energy. The steps of a reaction mechanism have to add up to the overall balanced equation, and they have to agree with the rate law. We can't prove a mechanism absolutely, but we can come up with possible ones. So if we're told a reaction is elementary, that means we use the coefficients as the exponents in the rate law. Elementary school is easy. Remember, you can write, just take those coefficients and put those as exponents. Okay, here we have a two-step mechanism. They have labeled the first step slow and the second step fast. They will always label them slow and fast. The first step, there will only be one slow step. That's your rate determining step. It's easy to write a rate law when the slow step is first. And that's what occurs most of the time. And so we write the rate law. Rate is equal to K times the concentration of NO2 to the first, because there's one of those, times F2 to the first, because the slow step was first. But if the slow step is not first, then you're going to have to use some algebra, because you cannot put an intermediate into a rate law. We don't have time to look at that right now, but your textbook may go into that. I know that the 10th edition of Zumdahl has that in there. They had removed it for a while. We got it back in there. But that may be asked once every 10 years. So not a huge priority. Okay, catalysts. Enzymes are biological catalysts. Platinum in a catalytic converter is a catalyst. They're going to increase the rate of a reaction by lowering the activation energy. And usually you're going to have a slightly different mechanism. Diagrams like this, or where you have to fill in part of this, have shown up on the AP exam multiple times. They may give you the catalyzed reaction and you have to draw the uncatalyzed, or vice versa. The important things, the catalyzed always has to have a lower peak, and they have to start and stop at exactly the same places. Because the delta E, the change in energy, does not change. But when you have a catalyzed reaction, because you've lowered this, your activation energy moves over here. This is a different kind of peak. This is number of collisions again. So you have more particles that collided with the activation energy. So your reaction goes faster with the catalyst. Okay, if you see this red line, how many steps does that reaction mechanism have? It has 4 steps. Which step has the highest activation energy? The third one. So which is going to be the rate determining step? The slow step. The third one. All right, we don't have time for the Nmsi super problem, but it is a good problem to work. There are several good problems on the end of this. We've got a few minutes here, because it's not going to take you 10 minutes to walk down 2 doors. But how are you feeling on kinetics?
Pretty good.
Decent. Okay, so if you were to look at a graph, how can you tell if it's a first order or a second order integrated rate law?
The graph of that
Some
straight line.
says
Well, if you're okay, have you learned CLR? Okay, and I don't have my graphics up here, but CLR is a cleaning product. You just remember that CLR, concentration, log, reciprocal. 0, 1, 2. If the concentration versus time is a straight line, it is 0 order. If the natural log of concentration versus time is straight, it's first order. And if the reciprocal of concentration versus time is straight, it's second order. CLR, 0, 1, 2. Because they ask that quite a bit on the exam. So feeling better about this, or like you do know this? You haven't taken your test over it yet? Ready for it? Have you done kinetics labs?
No, we're doing that next week.
Good, good. Okay, in a couple minutes, you'll be wandering 2 doors down. I haven't seen anybody come out yet.